So we'll be looking into the PV diagram of water. So just to study the PV diagram of water, we'll consider that we are doing the process in a reversible isothermal way. Okay. So there is a lot of counterintuitive things that are happening in this process. So just bear with it. We'll start with a very low pressure with a very high specific volume. So this is something like a rarefied state of gas. Okay, something that could be assumed to be an ideal, like where the gas behaves like an ideal gas. So at this point, we'll start compressing the gas. Okay, we'll start compressing it. We know that as we start compressing it, it's like molecules are going to come together. We are doing it very slowly such that the temperature of this thing won't increase. So we slowly compress it till it reaches a point. That is, it reaches a point where the vapor will become saturated. So it reaches like an instance where the vapor can be said to be saturated. Okay. So what is the distinction? What is the significance of this point is like if we compress it a bit more, like water tends to we get water droplets. Okay. So at this point, so if I name this point A and this point B, from point B, we are moving in this direction. From point B, even if we start to compress it, okay, our motive is to do everything in an isothermal way. So when we start compressing it isothermally, we find that the pressure won't drop or pressure won't go up. The temperature won't change. Okay, the only thing that is gonna change is the specific volume because we are having a phase change. So at from point B till a point C, which is the saturated vapor, saturated liquid point, that is all the vapor inside at point B gets converted to liquid without a change in pressure or a change in temperature. Okay, so as I said, this is very counterintuitive. It moves in this direction, which is point C. So from point C, which is at, let's see, liquid, saturated liquid. When we compress it, it stays liquid. Okay, we are increasing its pressure. Its specific volume is going to go down. Okay, for water, this goes up to a particular point. Okay, that's to some particular point. Okay, after this, for water, what happens is this point will have the highest density or the least specific volume. Okay, if we pressurize it a bit more, its density is going to go down, or its specific volume will go up. Okay, so it will move to a point like here, this point. This point, which will be somewhere here, which will be point, so that should be point E, which will be the saturated subcooled liquid line. from this point, if we increase the pressure at point E, if we increase the pressure, again, the same counterintuitive thing that happened between point B and C will happen. That is, the temperature won't change, the pressure won't change. We'll have a two-phased phase transition from the liquid to solid. So from point E to the next point. So we have at point E, we have the subcooled, the saturated subcooled liquid. So at point E to the next point, as I mentioned, that it is very counterintuitive. Pressure will not change, the temperature will not change, but the volume, the specific volume is going to increase. Okay, the specific volume will increase and reach a point F where we have the saturated solid. So after this, if we increase the pressure, its density is going to increase. That is, its specific volume will decrease and it goes somewhere here. Okay. So this is like what happens in a PV diagram or the phase transition, which this is how a phase transition is represented in a PV diagram. Okay. So as I've mentioned, in case of a TV diagram, this is common for different temperatures. Here the temperatures are kept constant. So here I'll have point B, here I have point A. Here I'll have point C. Go up, stay here. Go up, stay at some point, reach this point. This is E, this is F, this is D. Pardon the drawing. F, go to some other point. Okay. So if we join these points of interest here are point B, which is saturated vapor point C, the point where we have the saturated liquid, point E where we have the saturated subcooled liquid, point F where we have the saturated solid. If we join these points, we'll get a curve that looks like this. Almost similar curve. So we have the critical point here, we'll have the triple point line. So here we'll have the saturated solid line. And here we'll have sublimation line. Okay, so this is a locus of point B. The locus of point C is this line. The locus of point E is this line. The locus of point F is this line. So this is saturated solid. This is saturated subcooled liquid. In between these two, we have a mixture of liquid and solid. So we can see that we have an overlapping region. So between these two, we have liquid, and between these two, we have saturated. Between these two, we have a phase transition or a region where solid and liquid are coexisting in equilibrium. Okay. So at some points, we have a density overlap. Okay. So this is the sublimation curve, or the region of sublimation. This is in the sublimation curve. If we look at a PT diagram, we'll get a sublimation curve. Here we have a surface or a region where sublimation occurs. This region we have solid. Here we also have solid plus vapor. Here we have vapor. Here liquid plus vapor. I think in the phase, I'll have to make a correction. In the phase transition, I think it's a phase transition, our second video on phases. I've mentioned that in case of that TQ diagram, while undergoing like a sensible heat, I've mentioned that in case of like we considered everything for an isobar. So in that case, I have mentioned that the heat delta Q, say from A to B, can be founded by mc delta T. This isn't true because obviously this is thermodynamics. So heat by first law of thermodynamics is given by delta Q is equal to delta W plus dQ. So even if everything is done reversibly, du would be account for C delta T or mc delta T. So if I would drop the m term, I'll have the heat capacity rather than the specific heat. So heat capacity into delta T. So this is in specific term and PdV term. If we had considered the expansion, piston cylinder expansion. Okay. So this is PdV. So anyway, we'll have a change in volume. We'll always have a change in volume because we are putting heat into it. In case of water, there may be a region where the volume may go down because like when it is freezing till a particular temperature, we'll have density increase. That is, the volume will go down, shrinkage occurs. So we'll have to take into account this change too. Okay. So this is regarding the PV diagram.